Today we're going to begin Unit 6, which deals with centripetal motion. Centripetal motion is a little bit different than what we've been talking about before, which is linear motion. We've been working on things that are going in a line. So today we're going to ponder that eternal question. Can an object move at a constant speed and still be accelerating? And of course the answer has to be yes, of course, because otherwise why would I ask? That would just be ridiculous. Now, we need to look carefully at what the question is and is not asking. It would not be possible if I had phrased it, can an object move at a constant velocity and still be accelerating? The answer for that, of course, is no. That's just ridiculous. Why even bring it up? But the speed can be constant with an acceleration still occurring. And why is this possible? Well, again, we have to dissect the word accelerate. So we learned that in previous units that an acceleration is a change in velocity, any change. So we learned that if you're going faster, that's an acceleration. If you're going slower, it's an acceleration. It's anything that's a change in velocity. But we have to look at our definition of our word velocity. We learned that a velocity is a speed with a direction. So we had that speed and we had direction, and up until now, all of our directions have all of our accelerations have occurred because we changed the speed portion, but we kept the direction constant. So I was still going forward, but I was either getting faster or I was getting slower. And so I was changing the speed part, but leaving the direction the same. But what if we kept the speed part constant and we changed the direction? Would this still require a force? Well, anytime we change our direction, that does in fact require a force. And so you feel it happen. You never feel it happen when your forces are balanced. You do feel it happen when we have an unbalanced force that's causing that change in motion. So if you're sitting in an airplane flying at 300 miles an hour, you don't feel like you're moving. You feel like you're just sitting there stationary because all your forces at that point are balanced because you're traveling at a constant speed of 300 miles an hour. The only time you feel those accelerations are when you're speeding up or slowing down. And so anytime we speed up or slow down, then we feel that unbalanced force and we know that we've got this force happening. So anytime you feel it, that's a good indication that there's an unbalanced force going on there. So when I'm moving in a circle, do I feel that? And the answer is, of course it is. Anytime I turn a sharp corner in the car, if I'm riding on the Fissiksman, if I'm spinning around, I definitely feel this happening. So the question is, what way are we accelerating? Well, if we look at things in a line, that will help us figure out how things move when we're not going in a line. And of course, when I'm in a line, if I accelerate forward, my body tries to move backwards. If that light turns green and I floor it, my head tries to snap backwards. And that's just because, again, if the acceleration is forward, my head wants to feel backwards. On the other hand, when I slam on the brakes and I have a negative acceleration, my body moves forward. So that gives me the rule of I'm moving in the opposite direction as the acceleration. When I have a negative acceleration, my body wants to continue moving forward. When I have a positive acceleration, my body feels like it's trying to move backwards. Again, it's that whole inertia thing. Your body wants to resist that change in motion. And so my head is always going to move in the opposite direction as the acceleration. So the big question is, when I'm spinning around and my body is trying to move outward, then the acceleration must be directed inward. And this is where the word centripetal comes from. The word centripetal is a fancy Greek word that means center seeking. So whenever we have something moving in a circle, the only reason it is moving in a circle is because there is some force shoving inward on it. So we have this centripetal acceleration. And so again, the direction of the force determines the direction of the acceleration. So anytime I have a centripetal acceleration, there must be a centripetal force because F equals ma. And it works no matter what kind of force we have. So if we have a centripetal acceleration, it came from a centripetal force. And so Fc equals mac, it's the same concept we've been dealing with before. So the only way, again, an object can move in a circular motion is if there's something that's either pushing or pulling inward toward the center. And of course, if that force disappears, then the circular motion also disappears. And what reappears, of course, is going to be straight line constant speed motion. We naturally want to travel at a constant speed in a straight line. anytime we're not traveling at a constant speed in a straight line, there's some unbalanced force. That might be friction, it might be air resistance, it might be a centripetal force. So in this case, it's centripetal force. So if you're on some carnival ride and you're stuck to the walls, the only reason you're moving in a circle is because the wall is pushing inward on you. If the wall was not pushing inward on you, if we could magically make the wall disappear, then you would go flying off tangentially in whatever direction that you're at. So that's a very common example. If we have something and we're traveling around in a circle like that, and I'm looking down from the top, and these are all the people's heads that are stuck in this ride. As the ride is spinning around, then we are stuck against a wall, and it's great fun, and we feel like we're stuck, and it's fun. But again, if I made those walls disappear, then this guy would fly off that way, this guy would fly off that way, this guy would fly off that way, and this guy would fly off that way. They're all go tangentially. I think that would be the most fun carnival ride, is if we spun it around like that and then made the walls disappear and everybody went woo off to the sides. I think that one would be fun. But again, the whole reason that we stick to the wall there is because the wall is pushing inward on you. Since the wall is behind you, the only way it can shove you is in toward the center. So you feel like you're shoving against the wall. That's your inertia wants to go off in that straight line again. The formulas that we see here are, this is our generic centripetal formula for acceleration, and AC is equal to V squared over R. The V, of course, stands for speed. I know it should be velocity, but again, we're changing that direction, so really it's speed. So we have the speed squared divided by R, and R is going to be the radius. So the tighter the radius is, since that's at the bottom, if we get a smaller radius, we get a bigger acceleration. And so you may have noticed this when you're driving. If you take a corner and you're making a real sharp turn, you're going to feel that more than if you take a big wide turn. And so we have that going. So if we have, of course, F equals ma, if this is my A formula, to change it to an F formula, all I need to do is add an M. So to change the A formula into an F formula is just M times A. So we just add the M to the A formula, and we have an F formula. Now, sometimes we don't know the speed, but instead we know the period of rotation, how long it takes to go around that circle one time. That is called the period. And so the period, of course, if we're going at a constant speed, we want to use our constant speed formula. So V equals d over t, but if I'm going around a circle, the distance I'm traveling around that circle is, of course, its circumference. And the t, the time it takes to go around one time, is that period. So the capital T stands for period. That's a special type of time, the time it takes to go around one time. The distance, again, we said was the circumference, and so the circumference, of course, of a circle is going to be 2 pi r. So we're going to end up with V equals 2 pi r over t, and this would be a way to find out what is the speed. But of course, we can substitute this into the equation up above. So if we want to sub in, we have V is squared. So if V is squared, then we can shove that in there. And of course, everything in this formula needs to get squared. So 2 becomes 2 squared, which is 4. Pi become pi squared, which is weird because they're round. And r would become r squared, but the r on top is going to cancel out with the r that's already on the bottom. That leaves us just plain r, and t, of course, has to be squared to t squared. And of course, if I want to change that a into an f formula, all I need to do is add an m to that equation. Now, some people freak out a lot, and they say, oh, this top formula looks really simple, but the bottom formula looks really complicated. All we did was we added a 4 and a pi. And so 4 is always 4, and pi is always pi. You got a little pi button on your calculator, you just have to hit it. So realistically, the only thing I need to know on the top equations is I need to know the speed and I need to know the radius. Well, on the bottom, I still need to know the radius, but instead of knowing speed, I need to know period. That's the only difference. So I use the top equations if I know the speed. I use the bottom equations if I know the time, the period, the time it takes to go around one time. So that's the only difference. Everything else is just a constant value that's not going to change. That's very, very easy to do. Units, of course. We always have units for everything. So an acceleration is, of course, a meter per second squared, just like normal. Force is a Newton, just like normal. Everything works like normal, except period. Period, again, was a special type of time. So the time we have involved here is how much time does it take to go around in one revolution. So one time around the circle. So it's going to be in seconds per revolution. So no problem. If I see seconds per revolution, I think, okay, that's the big T. But sometimes when we're spinning really, really fast, we tend to write it as a frequency. And a frequency will tell you how many times you go around in 1 second, how many revolutions per second. So revolutions per second, obviously we have revolutions at the top, seconds on the bottom. We should have seconds on the top and revolutions on the bottom. It's just been flipped. So since that's an inverse relationship, if I give you something, which I will on your homework, if I give you something in revolutions per second, you need to say, hey, I need to flip that over. So 1 over that number will give you that. So if I have 5 revolutions per second, that's 1 over 5 seconds per revolution, which would be the period I need to plug into that other formula. So that's your little tip there, no problem. Here's our practice problem. Alex is driving recklessly around a corner with a 75-meter radius of curvature. She needs at least 4,500 newtons of frictional force to keep her 1120-kilogram car from sliding into the oncoming lane. What is the fastest speed at which she can make the turn? Well, typically what's happening is when you're going around the corner, the amount of friction you have is a lot bigger than the amount of centripetal force you need. And so this frictional force will keep you on the road, no problem. But if you keep going faster and faster and faster, eventually you're going to hit a point where it's not going to work. So there's going to be some point where the frictional force has to be equal to the centripetal force. Now, if the centripetal force I need, it becomes bigger than the frictional force, then I can no longer turn my corner the way I want to, and it's going to end up wiping me out and hurting me. So we don't want that situation. But here, the fastest speed at which I can make the turn would be the point where the frictional force is equal to the centripetal force. So of course we know 75 meters is my radius of curvature, so that's R. We have 4,500 newtons. Now that is the how much frictional force she needs. And so again, that frictional force is going to equal the centripetal force at this fastest possible speed. So the FF equals the FC here. 1,120 kilograms is the mass of her car. And of course, from that we can find weight and all that kind of stuff. But we're looking here for the speed, so the V. Now, which formula am I going to use? Well, clearly, if I'm looking for V, I need to use the formula that has V in it. So I'm going to use FC equals mv squared over r, but we need to algebra this for V. Now the V is already on top, so that stays there, but the m goes from the top on the right side to the bottom on the left side. R goes from the bottom on the right side to the top on the left side, and after that algebra, we would end up like that. And of course, eventually we will need to square root this to get rid of the V squared. So before we square root this, of course, we just stick in our numbers, and we end up with our FC times R divided by M. And if we do this, of course, we need to square root that answer. And after square rooting it, we find that the fastest she can go around that corner is 17 meters per second. If she goes any faster than that around the corner, then her car will not take the turn that she expects it to take. It will go off much straighter. She'll hit into oncoming traffic, and that would be very bad. So you got to be careful about that. What is her angular acceleration? Well, again, angular acceleration is just another way of saying centripetal acceleration. Sometimes that comes up where we phrase it differently. If we phrase angular acceleration, same thing as centripetal acceleration. So we could plug into an AC formula and we get the same answer, but I think it's easier to just use F equals ma. So A, of course, is F over m. So I'm just going to take the F that I gave you and divide it by the m that I gave you. And if you do that, of course, we end up with 4 meters per second squared. So that's it. That is the most acceleration that she is going to feel because she's moving around in a circle. Centripetal motion is pretty easy, and next week we will get together and we will show you a bunch of demonstrations on what it's like to turn around and spin around and the things that we feel and the things that we do, and we'll do some labs and you'll enjoy it immensely. But for now, of course, we need to do some practice problems. Of course, if I know time instead of velocity, we're doing the second formula. But by now, you guys are good with, I understand the process, I understand how to identify stuff, I know how to find the right formula that matches what I've got, and that's all I need to do is do the process that you already know how to do. So for homework, of course, you want to do problems A. So make sure that you get out your problems A sheet that I already gave you and get to work on those, and you shouldn't have any trouble with this because it's pretty simple stuff. And you guys are all super geniuses. So thank you very much. We'll see you later.